So we will wait for 10 minutes and then we will start. Okay, so you can start now. Okay, so welcome to the sixth. Yes, welcome to the sixth week of our course physics through computational thinking. And so, in the last tutorial video, in the last live session, so we talked about this how to solve defined kind of numerical method to solve first order differential equation. So we have learned about Euler method, RK2. It is called as a improved Euler method, RK4, and we also calculate the what is the order of the uh, error of local error and global error. So that we have talked about. So let me first briefly summarize. So in case of Euler method, so if we are given a differential equation of this kind, so dy dt, which is a function of y and t. So it can be anything like it. This function can be y to the power minus t y squared plus log of y, anything. So basically this is a function of this dependent variable and independent variable. So if we have this kind of first order differential equation, then how we can solve this for a finite time interval. So for this we know that if uh, ti is our initial time and tf is our final time, then we discretize this whole time series into a finite amount of data sets. So these are time intervals in which we will from which we will calculate how y changes as a function of time. So for that, the general scheme of Euler method. Uh, general scheme of Euler method is y in n plus one. So n plus one indicate what? So this is nth point, suppose, and this is n plus 1 point. So yn plus 1, it should be equal to yn plus function evaluated at that point, yn and tn. So this is Euler method. And in case of Euler method, we have seen that the order of local error. So if this the difference between these two time interval points, if this is h, then the local error is of the order of h square. And we have also seen that the global error is in the order of h. So this is for Euler method. And after that we have looked after RK2 method. So this similar differential equation, we can solve this via this RK2 method. And for RK2 method, the update equation, update equation is, so we define two new variables k1, so which is h of tn yn, and another one we have which is k2. So suppose this is n, because we are evaluating at this nth point, and k2n. So this is h function of tn plus h by 2 yn plus k1n by 2. And from this k1n and k2n, we can write down that y of n plus 1 equal to yn plus k2n. So this is for RK2 method. And we also have seen that in case of RK2 local error, this is in the order of h cube, and global error, it is in the order of h square. So as we can see that the order scale is improved from Euler method to RK2 method. So that is why whenever doing numerical analysis, if we use RK2 method instead of Euler method, it will give us better stability. So there are another method, RK4. So in case of RK4 method, so this differential equation, this can be solved by this following update equations. So here are four variables. So first one is k1n. So this is evaluated at tn yn, and after that we have k2n, which is function at tn plus h by 2 yn plus h k1 by 2 k1n. Then we have k3n, which is f tn plus h by 2, and here we have yn plus h by 2 into k2n, and after that we have k4n, which you can write as function of tn plus h yn plus h into k 3n. So from these four coefficients, we can write down that yn plus 1 will be equal to yn plus h by 6 k1n plus k2 2 into k2n plus 2 into k3n plus k4n, and tn plus 1 should be tn plus h. So this is for RK4 method, and in case of RK4 method, local error is in the order of h to the power 5, and global error it is in the order of h to the power 4. So that is what we have discussed in detail in previous lecture video. So so how to solve any kind of first order differential equation using this different kind of method. And as we can see that the error order is smallest in case of RK4. So that is why this RK4 method always gives us better stability compared to and better result. If we compare it with the exact solution, then RK4 will give us better result compared to this RK2 and Euler method. So, is there any question regarding this methods?
It's clear, sir.
Okay. Okay. So, this is for solving any first order differential equation. So, how can we solve any differential equations can be of any order. So, suppose we have an nth order differential equation. So, So this is an nth order differential equation. So n can be of any like 2, 3, 4. So and we have uh, a form of in the right hand side. So t x. So suppose what in case of harmonic oscillator, simple harmonic oscillator, our differential equation is d2x dt square equal to minus omega square x. So if there is no damping and no external driving, just then our harmonic oscillator equation leads to this. So this we can see that this is a second order differential equation. So how can we solve a second order or higher order differential equation using our known method of first order differential equation? So that we can do by the following way, that any differential equation, so any nth order differential equation that can be decoupled into n first order differential equations. So how can we do that? So let us take this example. So d2x dt square. So for simplicity, let us assume that omega is 1. So this will be equal to minus of x. So what we can do, we can define a new variable. So suppose dx dt, this is another variable which is v. So from this equation, we can write that d dt of dx dt equal to minus x, and this is our new variable. So this we can write down as dv dt equal to minus x. So what? So this is our initial equation, and from this second order differential equation, we got two equations. So this is our one first order equation, and this is our another the second first order equation. So what is the summary? So the summary is that we have this second order equation, and from that we can decouple it into two first order equation. So dx dt equal to v. In this particular example, the two first order equations are and dv dt equal to minus x. So these are first order equations, and we know how to solve a first order equation using Euler method or other RK2 and RK4 method. So so in that way in that spirit we can solve any number of any differential equation of any order by this Euler or RK4 method. So let us look at for Euler method. So we have our these two first order differential equation, that dx dt equal to v and dv dt equal to minus of x. So in spirit of this first order equation we can write that. So this can be of any function. So suppose in general we are assuming the general form here. So suppose this is a function of, it can be function of x, t and v in general, and suppose this is another function, and it can also be function of x, t and v. So we are solving for general equation. So we have these two first order general equation, and we want to solve this using Euler method. So what we can do, so in case of first order equation we have solved it via this update rule, xn plus h into function of xn tn. So in the same way, we can write here that xn plus 1 equal to xn plus h into function of xn, vn and tn, and this vn plus 1 will be equal to vn plus h, and here the function is different, so it will be g, xn, vn and tn. So as we can see here that this x n plus 1, it depends on vn, and vn plus 1 also depends on xn. So that means they are coupled. How x changes with time, that affects v, and how v changes with time, that vice versa affects the x. So for our given this example, what will be the update rule? So the update rule will be xn plus 1 equal to xn plus h, and the function is only v. So it will be vn, and vn plus 1, it will be equal to vn plus h, and here the function is minus x. So it will be minus xn. So vn minus h xn, and tn plus 1 will be equal to tn plus h. So this is the update rule for this Euler for this particular second order equation using Euler method. So we can generalize this idea to any to differential equation of any order. So third order, if we are given a third order differential equation, then we can decouple it into three first order differential equation, and we can solve it in the same manner as we have done for a second order differential equation. So this is for Euler method, and so let us look at what will be the update rule for RK4 method, because in principle in practically we are most of the time we will use this RK4 method because it has lowest order of error, so it gives us better stability. So, what will be the update rule for Euler method for RK4? So, for RK4, if this is our given equation, so then we have already seen that we can write this as 2n f of tn plus h by 2 yn h k1n by 2 k3n equal to f of tn plus h by 2 yn plus h k2n by 2 and k4n, which is f of tn plus h yn plus h k3n, and we can write yn plus 1 as yn plus h by 6 k1n plus 2 k2n 2 k3n plus k4n. So this is for first order equation. Now we have two first order equation. So one is dx dt equal to function of x, v and t, and we have another one which is dv dt equal to function another this function can be different in general, so x, v and t. So here for this differential equation we have to define this four variables, and for this equation also we will have another four variables. So let us write those down. So here we can write down that k1n, which will be x n, v n, t n, k2n. Yeah. So k2n, it this will be equal to tn plus h by 2 xn plus h k1n by 2 plus vn, and here we have to write down the k1n corresponding for v. So let me just write now here k1 prime, and what is this k1 prime n? So k1 prime n will be g of xn, vn, tn. So from these two equation, we these are our first coefficient, and from these two first coefficient, we can calculate the second coefficients. So this is one coefficient, and k2n prime, it will be equal to g of tn plus h by 2 xn plus h k1n by 2 and vn. Oh, sorry. So this will be comma vn plus h k1n prime by 2. So in the similar way, you can write down the other coefficients also. So k3n will be tn plus h by 2 xn plus h k2n by 2 vn plus h k2n prime by 2 and k4 k3n prime, it will be equal to g. So we are writing this case for this equation, and this prime ones are for this equation. So that is why whenever we are writing this k1n, k2n, k3n, we are using the function corresponding to the equation of x. So that is why we are writing here f. And whenever we are writing this formulas for these prime ones like k1 prime, k2 and prime, so this we are deriving from the second equation, and here the general function is g. So that is why we are writing here g. So it will be g tn plus h by 2 xn plus h k2n by 2 vn plus k2n prime by 2. And we can, and the last coefficients will be tn plus h xn plus h k3n vn plus h k3n prime and k4n prime. This will be equal to g of tn plus h xn plus h k3n vn plus h k3n prime. So from all these coefficients, we can write down that this x n plus 1, it will be equal to xn plus h by 6 k1n 2k2n 2k3n plus k4n, and we can write down v update equation as this: vn plus h by 6 k1n prime plus k2 into k2n prime plus 2 into k3n prime plus k4n prime. So these are the update. So this is for this second order differential. How we can solve this second order differential equation using this RK4 method. So what you have to write down, just you have to whenever you are doing numerical analysis, you have to just define the rule of you have to just define the functions, and after that you can automatically update this k coefficients, and from that you can calculate how this x and v this changes with time. So is this okay?
Yes, sir, clear.
Okay, so once we have we are done with how, like in how to solve these equations. So let us look at real examples. So first, so let us first look at driven oscillations. So what what are driven oscillation? So suppose you have a harmonic oscillator system. So it can be an LC circuit or spring mass system, and you are applying some force to the system. So the equation that we can write for is this: d2x dt square plus omega square x equal to f. So this is the force, external force, which you we are applying on the system. So this force can be of any type. So it can be a constant, just we are applying a constant force, or we can also apply a force which depends linearly with time. So with time the force is increasing. So if we look at the force profile with time, so it will increase. So that type of force we can apply. We can also apply quadratic force or any kind of force. So in general t to the power n, or we can apply some periodic force. So this if it can be of any, like, so suppose omega prime t. So we can apply any periodic force also. So this frequency, it may be it may be equal to this, or we can put different frequency also, and this force can be also exponentially decaying with time, it is about lambda t kind of force. So in general anything. So let us focus on this oscillatory type of force. What will be the case if we apply this oscillatory force to this harmonic oscillator? So for that force, our equation will be f0 cosine of omega prime t. So this omega is different from this. For now, let us suppose that this omega is different from this. So, and what you want to do? So this is our second order differential equation. We want to solve it using this Euler method or whatever RK4 method, and we want to see what is the behavior of this x with time, like with time, how our displacement or in case of LC circuit, it can be our charge. So how this parameters, it changes with respect to time. So for that we have, so this equation we can solve exactly. So there are two ways. One way we can solve any equation exactly, and another way by this numerical integration method. So let us try to solve this equation exactly. So as you can see that this is a in inhomogeneous differential equation. Okay, so before proceeding that, whenever we are doing numerical analysis with any given equation, so it is always useful to non-dimensionalize the equation. So as you can see here that in the equation, so this first term it has dimension of lt to the power minus 2, and from dimension analysis we can see that all the terms they have dimension of lt to the power minus 2. So whenever we are doing this numerical analysis, uh, it is always helpful to first uh, reduce this equation which involve this different dimensions to just non-dimensionalized equation. So that we can work with pure numbers only. So what is the how can we do that? So for that, for any given differential equation, first we have to see what are our what are our variables and what is our parameter. So in that case, x, t, omega. So these are our in principle, for x and t, this is our variable. So this has dimension of length and this has dimension of time. So if we can write x as l x bar. So here what we are doing. So suppose x is 5 semi. So this x bar, this is the pure number, and this L, this is 1 semi. So that means the dimension that is involved with X, that we are absorbing in the scale, and we are multiplying that scale with a pure number. So how can we, and similarly for time also, we can also, so if our, this is our time scale, then we can write this as T bar. So this is also a pure number. So first, you have to identify what is the length scale and time scale of a given problem. So as we can see here that from this equation and this equation, this has the dimension of L to the power minus 2, and similarly this F0 also has also should have dimension of L t to the power minus 2, because this cosine term, this is dimensionless. So so for this length scale analysis, what do you have to do? We can uh, this omega square. This we know that it is equal to k by m. So you can write down this equation as dt square plus kx equal to f0 cosine of omega prime t. So this kx dimension should be equal to f0 dimension. So from that we can write down that the dimension of x should be equal to dimension of f0 by k. So this is the length scale of our problem, because this f0 by k, it has dimension of length. So what we can do, we can write down this x as f0 by k. So this is the corresponding length scale with about which we were talking, and we can multiply it with a pure number. So this is our length scale, and this is the number corresponding to the value of x. So this is our length scale. Now we have to identify the time scale for our given problem. So here we can see that this from these two term, we can see that the dimension of first one is m l t to the power minus 2, and this kx, it has so that should be equal to the dimension of kx, and x has dimension of l. So t to the power minus 2, it should have dimension of k by m. That means k by m dimension is equal to the dimension of t to the power minus 2. So what will be the dimension of t then? So t will be root under m by k. Is it clear?
Yes, sir.
Okay. So we have identified our length scale in the problem. So one is f0 by k, which is our length scale, and the time scale is root under m by k. So and our given differential equation is this: dt square plus kx equal to f0 cosine of omega prime t. So what we can do now? So we can replace this x with f0 by k x bar and this t with root under m by k t bar. So let us replace them. So m, so x0, we will replace this with this x value. So f0 by k will come out, and it will be d2 x bar and the t bar square, and this t has it will m by k, another m by k will come out due to this t, and here we have x. So x we will replace f0 by k x bar, which will be equal to f0 cosine of omega prime root under m by k t. So these terms will cancel out, and f0 will be cancelled out from all the terms. So we are left with this equation: d2 x bar dt square plus x bar, which is equal to cosine of omega prime m by k. Okay, so this will be t bar. So this x and t, these are different from our initial xt. Our initial xt has dimension of scale, dimension of length and time, but this x and x bar and t bar, these are pure numbers. So this is just a simple differential equation. Now this as we can see, that time and frequency are have inverse dimension. So if we are if this is our time scale, then the frequency will scale by this 1 by root under m by k. So we can write this as root under k by m. So this is our frequency scale. In this equation, this still has a dimension of hertz, like the dimension of frequency. But if we replace omega prime with this value, omega into k by m, so the dimension will be absorbed in this, and this will be a pure number. So if we replace that, then we can see that this k by m will cancel out, and the equation that we are, so for, so let us suppose this is omega bar. So the equation that we are left with is this. Can you hear me?
Yes, sir.
Okay, so this is our given first equation, which involve the dimensions, and by this non-dimensionalizing method, so we are left with this differential equation, which only involves numbers. So this x bar, just we can replace this with x and t for simplicity of writing. So this is our non-dimensional equation, and this is the equation which we want to solve. So how can we solve this equation? So
Excuse me, sir. Sir, your screen is not shared.
scale is not shared. Oh, somehow it. Is it visible now?
Yes, sir.
Yeah. So From this equation, we got this equation, which only involves pure numbers. It does not involve any dimension. So now we want to solve this equation. Plus x equal to cosine of omega t. So this type of equation, these are called inhomogeneous differential equation. So how can we solve inhomogeneous differential equation? So we can solve this uh, as like you will uh, you can learn about this in any standard differential equation uh, course. So this we can write as a summation of complementary function and particular integral. So how we get this complementary function and particular integral? So complementary function we get uh, from the homogeneous part of this equation. So if the right hand side is 0, so this is our homogeneous equation for this corresponding inhomogeneous equation. And if we solve this equation, then we will get the complementary function. So how can we solve this type of differential equation? So this d of dt we call this as capital D. So this equation can be write as d square plus 1 into x equal to 0. So d square plus 1 equal to 0. So d is plus minus of I. And so if D has this two solutions, in general m1 and m2, if this is our solution for this equation, then we write complementary function as a e to the power m1 into independent variable. So independent variable is t here, and another so coefficient. So because this is a second order equation, we will have two uh, 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 coefficients, and this is m2 multiplied with independent variable. So in this particular problem, m1 and m2, they are plus I and minus I. So you can write this as a e to the power it plus b e to the power minus it. And in one of our previous tutorial video, so we have shown that this equation, this a to the power it plus b to the power minus it, we can write this as a another a cosine of t plus b prime cosine of t. Sorry, the b prime sine of t. So how we get that? So that can be easily solved. So this cosine we can write as e to the power uh, it plus e to the power minus it by 2, and this we can write as e to the power it minus e to the power minus it by 2y. And if we put this and do the just a little bit of mathematics, then we can find the relation between a b and a prime and b prime. So these two form, so we can write this solution as this. So this complementary function, this is a solution of this kind, a cosine of t plus b sine of t. Now we need to be given with two. So this is a complementary function. So for particular integral can be find out in this way. So 1 by d square plus 1. So because this is d square plus 1, and we have here cosine of omega t. So this we can write as uh, generally this d square uh, like should be replaced with this minus of omega square. So 1 minus omega square into uh, sine of omega t. So is this correct? So this cosine of omega t, this should be the derivative. So is this okay? Like, is this correct? Or it should be okay. So just check the formula for this kind of how to solve this kind of particular integral that we can easily see. So another way of deriving. So there is another way of deriving this particular integral. So that is by just doing a guess. So what we are doing, we are driving the system at a frequency omega. So what we can expect? So we can expect that after a very large time, the system will have a response which have frequency omega. So what we can do, we can assume the solution or the particular integral solution to be like this, uh, a constant. So we can write this as c and cosine of omega t. So we are assuming that after a long time, the system will forget about its initial condition and it will oscillate with the frequency with which we are driving. So what we can do? So this particular integral, it satisfy our differential equation. So that means we can put x as this, and from that we can estimate the value of c. So this so let us put this. So it will be equal to minus omega square c plus c into cosine of omega t equal to cosine of omega t. So it will be cancelled out, uh, and c will have value 1 by 1 minus omega. Yeah, okay, so I think this is right. So the value of c is 1 by 1 minus omega square. So so the final solution will be particular integral plus complementary function. So complementary function is this: a sine of t plus b uh, cosine of t, and 1 by 1 minus omega square into cosine of omega t. So this is our solution. And these two coefficients, how we can calculate them? So we can calculate them from initial conditions. So because since this is a second order differential equation, so we must provide two initial conditions. So the we can provide the initial displacement. So let us assume this to be 0, and we can also assume this in initial velocity, means dy dt at t equal to 0 to be 0 also. Let us check for this initial condition what will be these coefficients. So our complementary function is this: a sine of t plus b cosine of t. So at t equal to so if we put t equal to 0, we have with left with b, and this should be 0. So b is 0. So this is our one coefficient. And if we take the derivative of this, so we will get a t cosine of t, and b is already 0. So this is this is the velocity, and there is another cosine term. Hmm. And there is another, okay, so there is another term I just forgot to put. So at t equal to 0, we have this will to this by omega square equal to 0. So b should be equal to minus of 1 by omega square, and if we solve this, then we will get here minus bt sine t minus omega by 1 minus omega square sine omega t. So if we put t equal to 0 here, so we were left with this. So this this t equal to 0. Okay, so everything is going to 0. I think there is some problem.
So the first initial condition should be 1, right? Y at t equal to 0 equal to 1.
So you can assume that y of t equal to 0 and dy dt at t equal to 0 is 1. So this is also right. Like if we give both of them to be 0, then this is just the equilibrium condition. That means uh, the system initially at rest, like it has zero position, it has zero displacement, it has zero velocity. So if we don't drive the system, so it will just remain there. But if it has some finite velocity initially, then like if we drive the system, then I think it will give some solution. So just let me check. Okay, so let us take a 5 minute break. So in the meantime, just let me resolve the issue. We will continue
Okay,
after
sir.
5 minutes. ক্লাস করাচ্ছি। T equal to 0 should be v square sin of t equal to 0. Are you there? Mm, so,
Yes, sir.
yeah. So can I see? You can see my screen. Right?
Yes, sir.
Oh, so here I have done a little mistake. So this t should. So let me write down clearly. So the solution that we have is this: a sine t plus b cosine t plus 1 by 1 minus omega square cosine of omega t. So you can have different initial condition. So one you can have t equal to 0 and derivative, I mean velocity at t equal to 0, it can be 0. So this is one case. You can also have dy dt at t equal to 0 to be 1 and y at t equal to 0 to be 0. So you can have different kind of initial condition, and all of them leads to like just modification in this a and b coefficients. So dy dt at t equal to 0, it can be 0. So so we are evaluating this case. So let us look at this. So y at t equal to 0, if we put, then the first term it will be 0, and from the second term we will get b, and third term we will get 1 by 1 minus omega square. So that should be 0. So if we, from this we get our b coefficient, which is minus of this, and dy dt, let us evaluate this. So it is a cosine of t minus b sine of t, and from the last term we will get, so it will be minus, so minus of omega by 1 minus omega square into sine of omega t. So dy dt, if we put at t equal to 0 to be 0, at to be 1, then what we will get? If we put t 0, then we will have a, and this will be 0, and this will also be 0. So we will have a equal to 1. So our solution would be, in this, for this initial condition, our solution will be like this. So sine of t minus 1 by 1 minus omega square. So we can take this comma. So cosine of omega t minus cosine of t. So this is for our this initial condition. So similarly, you can do this for this case. So for this case, what will be the coefficients? So y at t equal to 0 is basically b plus 1 minus omega square equal to 1. So from that we get our b to be 1 minus 1 by omega square, and dy dt at t equal to 0, if we put this to be 0, then we will get a equal to 0. So in this case our solution will be 1 plus 1 minus 1 by omega square into cosine of t. So this is our b, and we have 1 by 1 minus omega square cosine of omega t. So you can write this as cosine of t plus 1 by 1 minus omega square cosine of omega t minus cosine of t. So similarly, you can also calculate for this case, and you can see what how this x and how this y and velocity. So from this y, we can also calculate what will be the exact form of the velocity. So is it clear now?
So, while considering the initial conditions, should we consider the particular integral part? Because it doesn't depend on the initial conditions, right? It is a steady state solution.
Uh, so this particular integral is basically for, so if we have any general non-homogeneous differential equation, then the solution of it will contain both the complementary function and the particular integral. So complementary function you can get from this homogeneous equation by putting the right hand side to be 0, and the particular integral, so you can calculate in this way. So this position, it is basically summation of these two terms. So that is why you need to consider the particular integral uh, when treating the initial conditions, because this is a summation of both the terms. So it is not like that this if what turns out that for large, if we look at large time limit, then the particular integral dominates. But this position, this is basically summation of both the complementary function and particular integral. So that is why like you need to treat both of them for evaluating these initial conditions.
Okay, sir.
Oh, so okay, so this is our exact solution, and we can solve this by doing this numerical integration method using RK2 or Euler and all this. So, uh, so for that, we have already discussed like this how to solve this equation. So these are there are core codes available. So uh, this is so this module, this one. So this is using this Euler method. So here what we have to do. So we are using this Euler method as a function here, and in that case, here we have four coefficients. So these coefficients. So it will be like how our the function look like. So let me just write down here. So our given equation is this: d2x dt square plus x equal to cosine of omega t. So what we will do for solving numerical method? So first we will write dx dt. We will decouple this into first order. So dx dt will be v, and dv dt, that we can write as minus of x plus cosine of omega t. So and we also know that d dt, it should be 1. So this all the three equation, this we will write down as a matrix method. So in like you can write down any number of differential equation in matrix form. So this we can write down as this. So ddt of dxv. Just first let me write down, and then I will explain. So here we will have 1 v minus x plus cosine of omega t. Yeah. So from this equation, these three equation we can write down as a combined single matrix form. So this is our suppose X matrix, capital X, which is TXV, and suppose this is our F. So this is 1V minus X plus cosine of omega t. So we can write down this equation as X derivative equal to F. So that we can easily see from here. So this equation we can write down as this ddt of dt, dx dt, and dv dt. So in the left hand side we have this, and in the right hand side we have 1 v minus x plus cosine of omega t. So as you can clearly see that these three equation, they are coming out from this single matrix equation, that ddt, this is 1, dx dt is v, and dv dt equal to minus x plus cosine of omega t. So we can do this for any differential equation. So let me give another example. So suppose we have this equation d2x dt square equal to 1 by x square plus mm, dx dt. Uh, yeah, so this is another example. So for that, how can we write down the single matrix equation? So we will follow the same procedure. So dx dt, first we will define this as v. Then from this equation we will get dv dt equal to 1 by x square plus v. So how, so what will be our x? Our x will be tx v, and our f will be 1 v and v plus 1 by x square. So, and with the matrix equation will be ddt of x, sorry, ddt of x, it will be equal to f. So is it clear? Like how can we write down this differential equation in matrix form?
Clear, sir.
Yeah. So in that way we can write down any differential equation in this matrix form. So so in this code, what you are doing, so this if, so this is basically our that if matrix, and for our given problem, the f matrix, we know that it will be 1. The first column, first row should be 1, second row is v, and third row is this minus x plus cosine of omega t. So if we are, if you are given with different differential equation, so what you will do, so we will just change the, like the element of this f matrix. So that will lead us to different differential equations. And after that, we are, so this is our initial condition. So this x0, it is basically uh, consist of, it will consist of three elements, because we are writing this x uh, as a matrix which has time, position and velocity. So that is why it it must have three elements. And in the here you can see that, this is our initial condition, this the initial condition that we are treating. So what is our initial condition? The first row is time. So we are treating the initial conditions at time equal to 0, and this is our position at time equal to 0. And see this 0, it is our velocity at time equal to 0. So you can put different initial condition, what you can just play around with it. And this tf, it is basically the final time, or the time up to which we want to see the dynamics of position and velocity, like how they changes. So this is our final time. And so this is our the number of points in time. So in, so what we are doing, we are discretize the time, whole time range. So these are the how many number of points will be there. So this is our in next. So in that module, what so if this we should give as in input. So we should give our differential equation form, we should give our initial condition, the time up to which we want to evaluate, and the number of point. So from that, this module, it will calculate the uh, uh, Euler integration method. So what we are doing here, so this is our time step, as you can see. So what will be the time step? Time step will be t final minus t initial divided by the total number of point. So this is our final time, and this x01, it represents our first row of this initial condition. So which is initial time. So that is why it is written in that way. Like in x, since x0 is a three core cross one matrix, so from that it will take the first value corresponding to first row, which is our time row. So if you are writing this as in a different way, like here we are writing this x as txb. So if you write this x as something like in this way, then our h will be t final minus this initial condition, and we should take the third element because this is our initial time, and we should divide it with number of steps, so n max or like whatever the notation is. Yeah, and what we will do? So while solving this Euler method for the whole time range, we also want to store the data. We want to store the whole time series. We want to store what are the values of x at different time, and also what are the values of this velocity at different time. So that means that is why we are creating a array here data. So this is our array, so this data list, and in this array we will we will insert the values at different times. So how can we insert this? We can insert this with the help of this append command. So append to it basically, so the array you have, it will append this value, like the whatever is the value of next, it will append to the data list. So so in that way you can calculate this x and v at different time, and you can append that to your data list or the array that you have created to store the uh, to store all these values of position moment, position velocity at time for whole time range. So the and so this is our update equation, which is so here we are using this Euler method as we have discussed. So this is our xn, like value of this x at previous step, and this is our time interval, and this is our the value of this function. So the value of this function for the previous value. So as we have seen for Euler method, go to that. Yeah. So here we can see that this x n plus 1. So this is the, and this x n, this is the value of the previous step, and we are evaluating the function at the previous points. So that is why so that calculation we are doing this through these commands, and after that we so after evaluating this, it will return the array. So is it okay?
Yes, sir. Clear, sir.
Yeah. So so this is the function for any general differential equation. Now what you have to do? So you have to specify what is the differential equation with which you are working, and what is your initial conditions. And so that means you have to specify these four quantities. So uh, so here what we are doing, we are calling the function, and this is our the form of this differential equation. So this the first column, the first row, it is 1, the second row should be v, and the third row it should be minus x plus cosine of omega t. So and this is our initial condition which we have specified here, and this is our time up to which we want to calculate, and this is the number of data point, like how many data point we are taking. Now since the error order for Euler method is uh, high compared to RK2 or RK4, So it is local error is of the order of h squared. So that is why we need more number of points to get a solution which will look like our original solution. Uh, but that is why we need large number of data points. So if we are working for the same problem using different methods like rk2 or rk4, then less number of data point like 1000 or 500 600 500 600,000. So less number of data point will give us better result compared to this Euler method. So anyway, for this Euler method, if we for this frequency value, if we put omega equal to zero point 0.9, and if we solve this equation, then this is the blue curve here. Blue curve is how the numerical simulation gives us the result, and uh, we we have calculated the exact solution of this equation for this initial condition. So this is our this uh, y equal to cosine of t plus. So this is our exact solution. So what we can do, we can plot it for for a t in interval like ti to tf, and we can compare with the solution that we get from the numerical method. So here you can see, so this red curve, it corresponds to the exact solution, and this blue one, it corresponds uh, to the numerical solution of Euler method. So as you can see here that the they almost matches with each other, but there there are some discrepancies like in that region from 60 to 75, as you can see, and also in the maximum values also where the derivatives are there. So the numerical method it fails to capture the essence of the original or the exact solution using Euler method. So what we can do, so we can use different method. So the different method that are available have rk2 method, or you can use rk4 method also. So this module, so this is for rk2 method. So like so in the rk2 method, what will be the different here? So we have to evaluate the function like, so let me go through the rk2. Yeah. So for rk2 method, first we have to evaluate these two coefficients k1 and k2, and after that we have to implement the update rule. So in the given code, so we 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 are doing that. So this is evaluated at the previous point, and this next point is what? This is the previous point plus uh, plus this coefficients like these coefficients tn plus h by 2 and yn plus k1 n by 2. So this we are getting from this next, and we are evaluating at that point, and from that we are calculating what will be the position and velocity at different time, and we are returning the like we are so this function will return the data list which will contain the array of position, velocity, and time. So for the same, so for the same differential equation and same initial condition, so we can solve the equation using this rk2 method. So as you can see here that this rk2 method and so this blue curve, it corresponds to rk2 method, and the red curve, it is the exact solution of the uh, of our system. So so what you can do, so as you can see that they are closely matching, so you can increase the number of data point, maybe 4000. Let me check. Okay, first we have to run this. We have to store the this function. Otherwise, whenever we will call this Euler improve, it will not recognize this, because if it is not stored, then this function will not be called, and it will not execute. So that is why first we need to store the function, then we need to specify this initial condition and our matrix, and we are defining here our omega and data list. So this is updated. So yeah, so as you can see that here with for this Euler method, even with 10,000 data point, so the numerical solution and exact solution, they are not matching. But using this RK2 method, for less number of data point, these two solutions, they are exactly matching. So that is why it is always advisable to use RK2, or it is best to use RK4 uh, instead of using this Euler method and RK2 method. So similarly, this is the code for RK4 method. So the the update equations and all this, that we have already discussed. So this code similarly, just so these are our four coefficients, and these are evaluating at the initial value, then this point 0.5 h by 2 into, this is our k1, this is our k2, from k2 we are getting k3, and similarly from k3 we are getting k4. And once we get all this, so we have to just implement the formula that we were discussing, this one, yn plus 1 equal to yn plus h by 6 k1 plus 2 k2. So this is how we are calculating the solution using alpha 4 method. So let me run that. So first we have to store the alpha 4 method. So as you can see here that this initial condition, let me make them same. So this should be 1, and this is, and so this is our initial condition. What we can do, let me just, okay, so it is running. So it is still evaluating, as you can see. So there may be some problem with my computer maybe. Okay, whatever it is. This is how we solve like any differential equation using RK4 method. So is this clear? Like there is some problem regarding my laptop maybe. So it's not.
It's clear, sir.
Yeah. Yeah. So this is for our driven harmonic oscillator. So what you can do, you can do the same with uh, different kind of forcing terms that we have seen here. So you can, if, so this is our equation plus k x equal to f. So f we can take simply to be f0. So if we do that, then, and we non-dimensionalize this, then the equation will be simply d2x dt square plus x equal to 1. So for that, what will be our, how to solve this numerically? So first dx dt should be v, and dv dt, it should be 1 minus x. So what will be our f? So f will be 1 v 1 minus x, and capital X will be t x and v. So let us check this for how the solution look like for this function. So we have to just replace this with 1 minus x. So this equation, it should be 1 minus x. So let me do that in case of RK2. So this will be 1. Let us check for this. Okay, so I don't know. There's some problem. So you got the idea, right? Like how to solve any differential equation.
Yes, sir.
Yeah. Okay. Okay. So I don't know. Like it's still evaluating. So maybe there is some problem regarding my laptop, maybe or something. But generally, it doesn't take that much time. Like it will evaluate within 1-2 seconds or so. So this is like the basic idea of solving. So in in that spirit, you can take any kind of differential equation, any kind of complicated differential equation. So what you can do, so there are other types of problems. So you can solve this LCR circuit equation also. So uh, LCR circuit is equation basically a damped harmonic oscillator. So also you can solve damped driven harmonic oscillator. So it will be a equation of this kind, plus kx, and there will be a damping term, gamma dx dt equal to f of cosine of t. So you can solve this numerically. So have you ever heard of this damping oscillator also?
No, sir.
So damping oscillator is basically so this damped oscillator as you can see here, that x terms it is linear, but so if we have differential equation of this kind, d2x dt square plus kx plus gamma dx dt, plus there is a nonlinear term of x plus beta x cube, um, may be driven say cosine of omega t, and you can also include nonlinear damping x square x dot. So any kind of complicated equation that you can take. So this is called the damping term. So you can read about it, this damping oscillator, uh, and this is nonlinear damping. So all these kinds of equation, what you have to do, you have to just dividing the equation uh, in uh, uh, first order equations. So let us do for this damped Duffing oscillator. Just so m d2x dt square plus kx plus gamma dx dt plus omega square x plus beta x cube plus eta x square x dot equal to f cosine of omega prime t. Oh, sorry. I have this term with extra. So just remove this. Yeah. So this is our equation. So you have, so first what you can do for simplicity, you can non-dimensionalize this, or you can proceed with the way as it is. So just for right now, let us proceed as it is. So what we will do, we will define v as ds dt, and our dv dt. So from equation 1 we will get m dv dt plus k v plus kx plus gamma v plus beta x cube plus eta x square, and this is x dot, so we can write down this as v, and here we have f cosine of omega t. So what is our differential equation for v? So dv dt is basically f cosine of omega t minus kx minus gamma v minus beta x cube minus eta x square v divided by m. So this is our second equation. So what will be our f matrix? So f will be this corresponds to the time, like what however way you are defining your x, t x b, or you can define other way also if you want. Then you have to just change the rows of this f matrix. So the first one is 1, the second one will be dx dt is v always, and dv dt, so it will be uh, f cosine of omega t minus kx minus gamma v minus beta x cube minus eta x square v divided by m. So what you can do now, you can just plug in all these three, and so so you can solve this either by non-dimensionalizing, that will be easy for computer to handle, but you can solve it in that way also, like you know your values of these parameters, this f, k, gamma, beta. If you know them, uh, you can just plug in their values, and just uh, write down the function, and write down your initial condition whatever it is, then you can get the solution of these equations. So there are other like projectile motion that you can also solve. So uh, mm, body falling under gravity, you can solve this without taking into account air resistance, or taking into account air resistance also you can solve this uh, rocket motion, like. So the idea is that any kind of differential equation, any equation, you can solve using this method. So is it okay?
Yes, sir, clear, sir.
Yeah. Okay. So I think this is enough for today. So we will meet next week.
Okay, sir. Thank you, sir.
Yeah.